In the previous presentation, we have seen that the expected value of the sample mean is what we want it to be. It's the expected value of the underlying distribution. We have seen that the variance of the sample mean gets smaller as we are increasing the number of measurements, which are all good things, but what we'd really like to have is we would like to have a way to really determine the probability of how likely it is to be for the sample mean to be how far off from the value that we actually want to measure. And whenever we want to compute probabilities, of course, we need a distribution, and so it is natural to look for the distribution of the sample mean, and that is what we're doing in this presentation, which leads us to the central limit theorem, which gives us at least the approximate distribution of the sample mean when we take enough measurements. So let's take a look at that. Let's first quickly review a random sample. That's a bunch of independent random variables with the same distribution. That's basically your repeated measurements in an experiment. That's the lowercase x k's would be the numbers that you get from that. Yep, repeated experiments. The sample mean is x bar equals 1 over n times the sum k equals 1 to n of the xk. And for a random sample, x1 through xn from a distribution with mean mu and standard deviation sigma, we have that the expected value of x bar is the mean of the underlying distribution, and the variance of x bar is the variance of the underlying process divided by n. And well, basically that means that a larger n will give us a smaller spread. That is correct. And that is the reason why it makes sense to repeat measurements. But it's still a challenge because in order to cut the standard deviation, which is the square root of the variance, in half, well, that would mean we take the square root here, so the standard deviation of x bar is sigma over square root n. So in order to get a denominator 2, we would need n equals 4, right? Because square root of 4 is 2. So to cut the standard deviation of x bar in half, we would need to quadruple the number of measurements. And that means there is a limitation to how much repeating measurements can do to improve the result. Typically, you don't repeat measurements more than 20 times or so unless you've got a really good reason for it. As a physics professor of mine once told me in a physics lab that I was taking when I was asking, well, so if I do this measurement 400 times, I get a lot more accuracy, and he just looked at me with, I think, a slightly sad look in his eyes, and he said, no, if you want to put in that much effort, you do much better in getting better equipment. Because once you've got better equipment, you get better measurement values with less spread to start with, and you then get better results that way. So that is something that certainly practitioners also have to take into consideration. Statistics help us to improve our measurement results, and certainly you don't want to just take one measurement because there's a chance it could be way off. But statistics don't fix bad equipment. Okay, so what's the theorem? Well, this is the first thing here. The first one here is not the central limit theorem, but if we have a random sample from a normal distribution, so we've got a process that is normally distributed with mean mu and standard deviation sigma, then for any n, the sample mean x bar is normally distributed with mean mu and standard deviation sigma over root n, so that's variance sigma squared over n. That's the same as what we already had worked out. We're not going to prove this result, but it doesn't feel too surprising because basically if you start with something that is normally distributed, well, then you should get something come out that is also normally distributed, and the mean and the standard deviation of x bar we had already worked out. So that's all right, and for quite a few measurements it's actually also quite sensible to assume that the values are normally distributed. But there's an awful lot of stuff like waiting times, for example, where the random sample we can be pretty sure does not obey a normal distribution. So what do we do there? Well, the central limit theorem says that if you take n values randomly sampled from an arbitrary distribution, so we don't care at all what the distribution is shaped like, and that distribution has mean mu and variance sigma squared, then for sufficiently large n, and that is another one of those terms that we're going to leave undefined, but as long as we take enough measurements, the distribution of the sample mean x bar is at least approximately a normal distribution, with mean mu and variance sigma squared over n. And again, we know that x bar will have mean mu and variance sigma squared over n, but we don't know the distribution. And the central limit theorem says that it's approximately a normal distribution. Now that approximately I can make precise, but you may not like it, because in some ways I don't like it either, because here's the precise statement. We're not going to work through the precise things. Basically what it is if you take your x bar, you subtract the actual mean, you divide by sigma over root n like we would do with a normal distribution, then the probability that that thing is between a and b, as n goes to infinity, that probability approaches a normal probability, and it approaches that normal probability in such a way that it really doesn't matter what a and b are. The difference between this and the normal probability will go to 0 at a uniform rate. Now that requires a lot of advanced concepts to just even understand what that means, and if you're interested in these things, we've got wonderful classes in real analysis that you may want to take. The proof of the central limit theorem itself is very, very complicated, and really I've read through it once as I proofread a book that a very esteemed colleague of mine was writing, but really a simulation actually helped me a lot more to understand what the central limit theorem does. And so now let me at least show you the simulation, and the simulation you can download from my homepage, and if I remember to do it after these presentations, I will also zip up the applet with the slides. But basically this is an Excel file, and I think you will really need Excel to make sure that all the macros work right. And so basically what I'm going to do here is I'm going to look at a population, and I want that population to satisfy this probability density. And if you want to play with the applet, you can adjust the probability to be as crazy or as simple as you want, and I've got a couple of standard distributions also. But what we can certainly say is this is a population, this is a probability distribution where you've got a big chance to be around 9, a big chance to be around 3, certain chances to be anywhere else, but that is definitely something that doesn't look like a normal distribution, right? Because a normal distribution doesn't have 2 humps, it just has 1. Okay, so if I now take samples from that population, well, then I just compute a population of 1,000 samples, let's say, and what we of course always say is the probability predicts the reality. And so if I sample a population of 1,000 individuals according to this probability density, then I'm going to get a lot of individuals around 3, a lot of individuals around 9, and then accordingly fewer individuals around the other sizes. And basically the blue, I think, is the probability. It would be the perfect population that would be exactly 40% around 9 and exactly 29% around 3. And what we're having is, okay, the gray one is the ideal one. The real one actually is that in this sample I have 286 around 3 and 415 around 9 rather than 401. Well, if I were to hit this again, I get a different population. Now I've got 406 around 9 and exactly 290 around 3. Of course, there's nothing that forbids an exact hit, but no matter what I do, the population will be close but not exactly equal to what I would get from the ideal population if it was exactly the right percentages. Okay, so now typically I don't see the whole population because I cannot take measurements forever, or it may just be not feasible to query 1,000 individuals. And so what I typically do is I take samples. I ask one person out of the population. And of course, if I ask one person out of the population and compute the average, that's not going to tell me much. That's not going to capture the spread. And so on this third sheet here, I basically just talk about samples, and I take the averages of the samples. And what I'm doing is I think I'm taking something like 100 samples or so. Yeah, I'm taking 100 samples. And if the sample size is 1, well, then the individual samples just tell me, okay, individual 76 has gave me a value of 9, individual 75 gave me a value of 3, individual 74 gave me a value of 7, and so on and so on. And of course, as long as I have only one number, the mean will be just that number. And that means that if I look at my sample averages, and if I look at how they are distributed around the mean of the population, which is around 6.47, well, then what the central limit theorem wants is a normal distribution, but with one sample. Of course, I'm not getting anything that looks anywhere near normal. But that's also not to be anticipated because the central limit theorem says for sufficiently large n. So let's take a look at what happens when I take a sample of size 2. Well, when I take a sample of size 2, then my 74 sample now contains two individuals. One returned a value of 7, the other one returned a value of 9. If I look at my 73rd sample, I get two numbers here, and so now the average is no longer one of these two numbers, but it's the average of these two numbers. And if I make a histogram of those averages, well, it's still not quite normal. Remember, the red part here is the idealized normal population that we should get, but it starts looking at it as if it has only one hump, and that's already pretty good. So now if I take a sample size of 3, well, that means that I can have things like two individuals giving me 7, one individual giving me 3. If I look at the 72nd sample, it spreads out a little bit. Let's see if we can find one. Yeah, here we have a sample where 3 individuals give me 3 different numbers. There are probably also samples where 3 individuals give me the same number in here. But we're just averaging things out, and as we then look at that around the population mean, which remains at 6.47, the red is what an idealized normal distribution would be. And now we're getting to see something here. This looks like the hump of a normal distribution, right? And so now what the central limit theorem says is that the fit between the theoretical prediction, this red normal distribution, and this blue distribution of the sample averages, where I'm just computing a histogram of the sample averages, that fit is going to get better as I increase my sample size. And so if I take a sample size of, I wanted to have 10, I think, well, visually the fit is looking better, and if I look at this histogram which tells me the differences, those differences have gotten smaller also, because the biggest difference we have is a downward deviation of 4.7%. Previously we had one that was a whole lot bigger, and so now if I take a sample of size 20, my deviations are again overall smaller, I get a better fit. And then if I were to just recompute the samples, okay, here's where I was unlucky. I got an undershoot of 10.8 theory versus practice, so that can happen too, and that's why the central limit theorem says it's only approximately, right? And if I now look at a sample size of, say, 40, well, then I get a better fit, and now if I recompute the samples, my fits, well, they're still every so often not that good. Man, that's terrible here, and that, my goodness, it's really not getting any better here, right? Okay, now here I have one situation where my samples are better. So basically what that says is that if I were now to take repeated sample averages, then these distributions will look more and more alike, and if I take a really big sample averages, yeah, okay, they're starting to look more alike, and now all of a sudden here, overshoots and undershoots by 7% and about 5%. That's really not that bad, because we had seen for sample sizes of 40, we still could get some pretty bad overshoots and undershoots, and now with a large sample size, that doesn't really happen anymore, but there are still deviations. And so that is the kind of thing where in the central limit theorem people say, okay, if we're in large enough, we can get an approximately normal distribution, and part of these overshoots and undershoots is that we can't expect to get an exact match because the blue distribution will only be approximately like the red distributions that I've compared it to behind that. Okay, I hope that helped a little bit. One of the things that I am certainly always concerned with is whether I'm understanding the central limit theorem now better because I've run the simulation or because I've written the simulation. I can certainly tell you that nothing beats experience in working with data. That's why maybe in some classes your teacher will come in with dice and say, okay, let's roll those dice. Let's have 50 people get me sample averages, and then look at the distribution of those sample averages to see that even though when you roll dice, of course, you've got a uniform distribution, the sample averages start looking like a normal distribution if you set up the right kind of histogram. That just gives you more of a visceral understanding as to what the central limit theorem does. And the amazing thing really is that unless you've got a rather pathological process, these sample averages just end up setting up these kinds of bell curves, and that is really why that is one of the big reasons why the normal distribution is so frequently occurring in data analysis, because the most elementary data analysis process, take the mean, is governed by, at least approximately, is governed by a normal distribution. Now let's take a look at what we can do with examples. Okay, first a quick rule of thumb really. For n greater than 30, the central limit theorem can be used, which means for more than 30 samples, you just assume that your underlying distribution is normal. That is not hard and fast. I've used a different text where the author said make n greater than 40. I'm pretty sure there may be some texts where people say n has to be greater than 20 or something like that. And in fact, I think I've even published it. I've published a paper where I looked at a very pathological process that was pathological in the sense that it doesn't obey this, but it was a situation that actually occurred in my area, or could occur reasonably in my area, where the central limit theorem didn't kick in for samples of size that have sizes in the millions. So something like that can also happen. Thankfully, for lab type measurements, typically these kinds of rule of thumbs are pretty good. Okay, so now we ought to get to examples. Let's take a look at the mean daytime high temperature on a randomly chosen summer day in a certain town, and let's just say that that mean daytime high is 95 degrees Fahrenheit with a standard deviation of 2 degrees Fahrenheit. Compute the probability that the average daytime high over 36 days is greater than 96 degrees Fahrenheit. Okay, so now with this process that I recommend in my book, that you always think about what's your random variable, what's your underlying distribution, what are the parameters, and what is the probability that you're interested, or what is your event and what is your probability. The random variable here, of course, is the average daytime high temperature T bar, but remember it's the average, so it's the thing that potentially is governed by the central limit theorem. The event is that T bar is greater than 96. The distribution, approximately normal because we've got more than 30 days, and the mean is 95, and the standard deviation now is 3 over root 36. That's a typo. Let me fix that real quick. And we're back. I actually wanted to have that the problem is stated with a standard deviation of 3 degrees Fahrenheit, and so now by the central limit theorem, you take the mean of the underlying process, you take the standard deviation of the underlying process, and divide it by the square root of the number of your measurements, which is square root of 36, and that of course now means that the standard deviation is 1/2. That's a nice number, and of course it's a made-up problem here. The probability is what we want to determine, and so that means we're interested in the probability that T bar is greater than 96. Well, what do we do with a normal distribution? We subtract the mean, we divide by the standard deviation, so we get 96 minus 95 divided by 1/2, which will give us approximately the probability that a standard normal random variable, because this is approximately a standard normal random variable, is greater than 2, which is 1 minus the probability that the standard normal random variable is smaller or equal than 2. You look that value up in a table, that's approximately 1 minus 0.9772, which means we get that this is equal to 0.0228. And so that would solve this problem. Well, the interpretation is that statistics cannot predict the temperature on a given day, right? But we can get reasonably good predictions for the average temperature over a number of days here. And of course, weather modeling, which tells you what the temperature is going to be tomorrow, it does involve statistics, but it's much more sophisticated than what we can do at this stage, because it involves actually by now GPS positioning of storm systems and the like, where a lot of stuff is statistical and then a lot of stuff is deterministic with a slight statistical component, because you can predict the paths of storms, at least where you think it's most likely to go, and then you can say it's less likely to go in certain directions, and that gives you usually then a temperature range for certain places that are more or less far away from where that weather system is moving. Okay, so let's take a look at an example where we're looking at manufacturing candy, and the fill weight per bag of this candy that we're making has an estimated standard deviation of 2 grams. Okay, so we're still going to estimate the standard deviation, but we're going to go in the direction of determining what the mean is. So we want to know how many bags should be weighed to obtain a sample average fill weight that with 99% probability is within 0.5 grams of the actual mean fill weight. So we want to set up a process so that this sample average that we're going to measure has a 99% chance to be within 0.5 grams of the actual mean weight, and that is then the kind of thing that you do in quality control, because you would sample some bags and hopefully you'll enjoy them too. But you would sample, you would weigh them. I'm not sure if your employer would actually let you eat the stuff. They probably just weigh it and put it back on the conveyor belt. But nonetheless, that would tell you whether your fill mechanism has a small problem or so, where maybe it's slightly underfilling or slightly overfilling. And of course, you want to do that with a sequence of samples, because it could be that the mechanism is off, but by accident you grab a bag that is just filled to about the right weight. Okay, so what's our random variable? Our random variable is the sample average fill weight, W bar. The event is that the sample average fill weight is within 0.5 gram of the actual mean fill weight, which means if we call the actual mean fill weight mu, then our event is that the absolute value of the difference between W bar and mu is smaller than 0.5 gram, right? Within 0.5 gram means we at most overshoot or undershoot by 0.5 gram, and that means that we need to look at the average value of the difference. The distribution, we're assuming an approximately normal distribution with mean mu and standard deviation sigma over root n, because that's the best working assumption we can make. If it turns out that our determination gets us an n that is too small, you can always sample more than 30 bags, even if this just requires you to sample, I don't know, 10 bags or so. Or maybe you've got a good reason to assume that your underlying distribution is normal, in which case then the smaller n would work just fine. And well, sigma over root n is 2 grams over root n, where n is the number of weighed bags, and that's what we need to find. The probability is given as 0.99 or 99%. And so now we turn that into a probabilistic equation. The probability that W bar minus mu is smaller than 0.5 gram has to be set equal to 99%. And we do the same thing as before, right? We already have subtracted the mu, so we divide by the standard deviation. So the 0.5 gram is divided by 2 gram over root n. And that means, because W bar minus mu over sigma root n is z, we get a z bar over here. We get a standard normally distributed random variable. Computation here is, of course, just 1/4 root n. So we need to figure out an n so that the probability that z bar, the absolute value of z, is smaller than 1/4 root n is 0.99. Because of the symmetry of the normal distribution, that means that we would have 0.005 probability in the right tail and 0.005 probability in the left tail. And so if the right tail has a probability of 0.005, you can draw that. Well, then the probability to the left of this cutoff here would be 0.995. That's a picture that I really want you to draw to understand, and I don't have an animation here to set that up. But it's a good thing to get yourself reconnected to normal distributions here. And so what we're interested in is a value of n, so that the probability that a standard normal random variable is smaller than 1/4 root n is 0.995. All right, we look in a table and we realize that the probability that z is smaller than 2.58 is approximately 0.995, and so that means that this value here has to be approximately 2.58. And that's what we'll see on the next panel. We now take our 1/4 root n, set it equal to 2.58. That means that square root of n is 10.32, and that's even exact, right? Because 4 times 2.5 is 10, and 4 times 0.08 is 0.32, all right? And now n would be 10.32 squared, which is approximately 106.5, and so that means n greater or equal than 107 should do it. We always realize that these are lower bounds, so even if this had been 106.1, we round up. And well, that is it already here. Now, I think the next thing we're going to do is we're going to interpret that a little bit. So what would the measured value actually tell us? Suppose in the previous example, the sample average of 107 measurements is 252 grams. Does that mean that the actual mean weight is with 99% probability between 251.5 grams and 252.5 grams? And it's very tempting to say yes, because that's how we set things up. But if you actually analyze it, and this is something where at first I had a misunderstanding with that for a long time, and it is rather subtle, but if we look at that, the actual mean is a number and it's fixed. And as soon as we give a range, say between 251.5 and 252.5 grams, the mean is a number, and as soon as we give a specific range of numbers, that actually mean is either within that range or it is not. There is no probability involved. So the answer must be no, because it either is or it isn't. There's no probability involved anymore. The fact that we don't know doesn't enter the consideration there, right? It's basically similar to the fact that I don't know the lottery numbers for next week's drawing. That doesn't change my probabilities in any way through any kinds of analysis. The numbers are going to be what they are. So that is kind of strange, right? Because we set all this stuff up and talk about probabilities, and in the end, we still get an answer that is yes or no. So why do we measure these sample averages at all? Well, this is a clash between the intent and being formally correct. And what we can say is that under the assumption that the actual mean is not in the range that we've given above, it would be very unlikely to get a sample average of 252 grams, because a priori we would only have a 2.3% chance to get such a sample average, yes. And so, whereas we cannot assign a formal probability to the actual mean being between 251.5 grams and 252.5 grams, we can have a certain amount of confidence that it is, and that really leads in the direction of analyzing and computing confidence intervals, which is what we're going to do in one of the following, and probably even in the next presentation. So moving on right now, let's take a look at one more example. Let's take a look at the time that it takes until a certain given pain medication reaches maximum level in the bloodstream, and suppose it's been measured in 36 patients. The sample average time was 20 minutes, and the standard deviation was estimated as 3 minutes. Oh my goodness, I've got pretty much the same numbers there, I guess, but there's only so much I can do with that here at this stage. I want to determine the likelihood that the actual mean time to maximum level in the bloodstream is greater than 21 minutes. Well, okay, to do this, I would assume that the actual mean is 21 minutes, or greater than 21 minutes, and compute the probability of obtaining the above sample mean. So my random variable is the sample average time to maximum level in the bloodstream. The event is that if we're assuming that the mean is greater than 21 minutes, we want to compute the probability that t bar is 20 minutes. And the event then is that t bar minus mu is smaller than 20 minutes minus 21 minutes, which is -1 minute. And the distribution is normal. We're assuming the central limit theorem holds here or applies, with mean mu and standard deviation 3 minutes over root 36. I think I used those numbers to make sure that I get pretty numbers here. And that's 1/2 minute, of course. And the probability is to be determined. Alright, so we do the probability computation. So the probability that t bar minus mu is smaller than -1 minute. Well, we turn that into something normal, right? We already have subtracted the mean. So that would be that we now have to divide by the standard deviation, which is sigma over root n, which is 1/2 minute. And so that's approximately the probability that z is smaller than -2, which is the probability that z is greater than 2, which is 1 minus the probability that z is smaller than 2, which is 1 minus 0.9772, which is again those 2.3% here. So that turned out to be very similar numbers, but basically what that means is that I would not have much confidence in any claim that based on the measurement, I would not have much confidence in the claim that mu would be greater than 21 minutes. And this is now basically the starting point to a bit of philosophy, a bit of something that could actually, to the untrained eye, feel kind of could make us insecure a bit. So what you can do here, of course, in terms of computing, in terms of getting used to things, is that you can solve problems that are like these examples, but basically you also want to interpret them, because basically what it means is your measured value is what it is, and the exact value of what you want to measure is what it is, and they're either far apart or they're not. As long as you've got two numbers, that's all you know. It's just that if you have a measurement that is a measurement of 5, let's say, and the standard deviation of your process is very, very small, well then it is very unlikely, it would have been very unlikely for you to measure an average of 5 if the underlying mean actually is something like 12 or so. And so based on that reasoning, we can then assign a certain reliability to our measured values. Based on that, we can say, okay, 68% quote-unquote chance that our exact value is within 1 standard deviation, within 2 standard deviations, within 1 standard error, which in 2 standard errors, within 3 standard errors of the measured value. But again, it is actually, what we're actually assigning is not a probability. What we're assigning is a confidence level. And we're going to talk about that in our next presentation, I think, on confidence intervals. All right.